Hello friends, my name is Vivek Sharma. Today we can cover this interesting problem that's called all nodes distance k in binary tree. So in this problem we have been given one binary tree with a root node and a target node and an integer value that's called k. Okay, and we need to return a list of values of all nodes that have a distance k from the target node. So I'm just reading this problem statement. So let's try to understand this problem a little bit. So I copied this diagram to this whiteboard and let's try to understand what does it mean. So this is the given tree, okay? And this yellow color, this is target, right? So 5 is target here, okay? And now the value of k is 2, right? So k is the given distance that this is the how much distance we can cover from the target node, right? So let's see. From 5, if we go down from 5, then we can cover this is one distance and this is one distance. So this is basically here the distance means the number of edges we can say, because this bridge between two nodes is an edge, right? So how these two nodes are getting connected. So if I will travel from one node to another node, then I have to cover one edge, right, at one time. So that's how I will cover the distance, right? So 5 to 2 is one distance and 2 to 4, that is two distance, right? And then again 5 to 2 one distance here, and then 2 to 7 is another distance, right? So 5 if I have to calculate like distance wise, then these are the two distances, and the 7 and 4, they are two distance apart. So basically my output would be 7 4 if I go down. Why not 6? Because 6 is not eligible for the output because it's only the one distance apart, right? So this guy is only one distance apart. All right, so now let's go upwards as well, because we can go down and up as well from the target node. So if I go up, this is 3, this is one distance apart, and from 3 there is again one that is also one distance apart. So total distance is from 5 to 1 is 2, right? So 7 4 2, these are all the eligible nodes that we can return as a result, right? They all are the two distance apart from target node, that's called 5. All right, so this is how we can understand this problem. Now let's try to collect couple of observations and facts. And why we want to collect those observations and facts? Because based on those observations we will build our algorithm and we will try to solve this problem. Okay, so let's do this. So if I oops if I come to this page and we carefully look this diagram here, right? So target node, this is target, and the k is 2, right? So k is 2. So generally in binary tree traversal, what we do, we just follow the top down approach, means we start our traversing from the root node and we go down, right? Generally, not every case, but general, that's how we do the traversal, right? But in this case, because the target node, it's not necessary that it will always be root node. It can be in the middle as well in the tree. So that's why we can go either up or down as well, right? And that's why we are adapting both the direction from the target node, right? So this is the important observation, and from that observation we can conclude, or we can just we are just coming to that conclusion that we are going up, then it means we have to keep the track of the parent node as well, right? And that is the important fact. So we need to keep a track of the parent nodes, right? So this is one observation, and that's important, right? So why we need to keep a track of parent nodes? Because by calculating the nodes, 7 4 is the one set and 1 is another set. And how we reach to 1, right? We reached through parent. From 5 we started our journey, and then we reached 5 parent, that is 3, and from 3 we again go to child of 3, and then that's how we reach to 1, right? And that's how we covered distance 2. So parent node, that's one observation. Second observation is basically we are just traversing one by one, right? What does it mean one by one? So if you see, like from 5 we are going down, and then just we are checking one distance apart all the nodes, right? 6 and 2. and we are checking, okay, it is only one distance, let's go again further down. We cannot go further down to 6 because this is null, right? And but we can traverse the children of 2, that is 7 and 4, so that's why we will go another level down, right, from 2, and that is 7 and 4, right? So what does it mean by one is we are one way we are just traversing level by level, right? So one level and another level, and similarly we are going up direction as well, one level and then another level, right? It can be any direction, it can be upward direction or down direction as well. But what we need to do, we have to traverse all the neighbors. So for example, if I am at 5, right, if I choose different color here, the blue color maybe, if I am the target node 5, then I have to choose, I have to choose and traverse the neighbors of 5 itself, right? What does it mean? I have to traverse the neighbors means I have to go down, and 6 and 2 they are neighbors, and 3 is another neighbor, right? So if I do this, if I traverse, if I see all these neighbors, then I have to go again the next neighbor, right? So next neighbor is 7 and 4, and the for 3 neighbor is 1. So that's how I will go neighbor by neighbor, right? It can be upward direction or it can be downward direction. Simultaneously I have to traverse all the neighbors. It can be in any direction. So for example, for 5 I am just choosing 3 and 6 and 2 because that's the one level up, one distance apart from target node 5, right? So here really the key is basically I am traversing the eligible neighbors or not. They can be anywhere, right? So at, if I am traversing the neighbors, then I'm good. So what essentially I'm doing here is I'm traversing all the eligible neighbors, right? Level by level. And this property is basically uh, we apply the breadth first search, right? So breadth first search, in the breadth first search we apply the same property, and that's how we use the breadth first search. So important fact here is BFS, breadth first search. So if we know these two observations and facts, then we can try to solve this problem. So once, first of all, let's keep track of the parents of each and every node, and let's apply the breadth first search. We will start from the target node, and we will traverse, basically we will just traverse all the eligible neighbors one level by level, and then we will, once we are able to traverse the all the neighbors, and once our level is 2, for example this distance is 1, right? If I go to different page, so for example this distance is 1, once I traverse 6, 2 and 3, so one distance, and then if I increase my distance after coming to 7, 4 and 1, then if I say okay, my distance, and that is equals to k, then what I will do, I will return my these eligible nodes, that is 7, 4 and k. And how will I return this? So let's try to quickly walk through that as well, right? So let's walk through that thing. So what we can do, let's say this is our queue, right? So in the queue, what we will do, we will first of all we will just oops, what we will do, we will start with the 5, right? We will insert 5 in our queue, right? Why we are inserting the 5? Because this is the target node, and from the target node we need to determine that what are the nodes that we need to get from the k distance apart, right? So definitely we have to start from the target node. Now we will poll from the queue, right? So we will get that node from queue. Why we are getting? Because so that we can check the parent and the child node. Now we have to traverse all the eligible neighbors, right? So all the eligible neighbors is 6, 2 and 3, right? So we will check, okay, is there any left or right child? Yes. So 6 and 2 we will put in the queue itself. And is there any parent? Yes. So we will put 3 as well. Okay. So one label is done. So let's say initial our label was 0, and now after putting 6, 2 and 3, what we will do, our label we will become, it will become 1. Okay, nice. Now we will poll 6. Is there any children or parent of 6? So children is nothing, so we cannot put anything into the queue further, but parent is 5, and 5 we already visited, right? So we will keep track of visiting as well, because the thumb rule is whenever we are doing depth first or breadth first, we have to keep a track of visited nodes as well, right? That is the thumb rule. Why we need to do that? Because in these kind of the traversal, there is a there is a very high chances that we can visit one node again and again. So we need to make sure that we are not visiting one node again. So that's why we just keep a track of visited. So in this particular problem and this particular solution, we would maintain some auxiliary array or different mechanism to keep a track of the visited as well. So let's make sure that 5 we already visited, so we are not going to insert that again in the queue. And then basically we will go to 2, so we will poll 2. And is there any children? Yes, so 7 and 4 we will put here. Is there any parent? Yes, 5 is the parent of 2, but that's already visited, right? So we are not going to put inside the queue. Okay, so now after so what we did here, and now remaining is the 3, right? So what we did, and initially we put 5, right? After putting 5, so before putting 5 basically our level was 0. After putting 5, after polling 5 and 6 to 3, after putting all these 6 to 3, now 3 is also remaining, right? So 3 is also remaining. Let's poll 3 as well from the queue. And after polling 3, what we can do, we will just check the same manner. Is there any parent? So is there any parent? There is no parent. Is there any children? Yes, but 5 is the children child of 3, but that's already visited, so we are not going to put it again. But 1 does not, we did not visit and we did not put into the queue. So what we will do, we will put inside the queue, right? And then after putting all this thing, right? So now after putting 741, we cannot go further to 1, right? Remember, we are going step by step, level by level. So after our queue is empty, right? After our queue is empty, now basically, so let me do this actually. Let me make it more clear. Otherwise, it might be confusing for some of the people, right? So uh, let me make it some. First of all, let's say label is 0, and this is queue, right? Internal queue, and then 5 is there, right? 5 we poll, and then we put 6, 2, 3, right? That's what we discussed earlier, right? And now after putting 6 to 3, this is level 1, so we just increase the level 1. So this is level 1 queue, right? This is level 0 queue, this is level 1 queue. Now we will be polling all these guys 6, right? And then this is level 2 queue. This is a little bit easier to understand, right? I'm not messing up with only one queue. Why I'm taking this is literally one queue only, but this is easier to understand, right? So 6 we will not uh, pushing anything, or we will not be not pushing but inserting or offering into the queue, right? Push we use generally for the stack, but for queue we use the offer or add word, insert keyword, right? Or these are the methods that we use. Just a naming convention, nothing big deal. So similarly for 2, because for 2 we are having 7 and 4, so we will insert here 7 and 4. For the 3 initially, so for 3, 5 is already visited, we will put 1, right? So this is the second level. Now we will increment again our level equals to 2, right? So what happens that once this level is equals to k, we will immediately return this list 741, and that's it, right? So this is the idea, and this is how we can solve this problem. So let's do this. Let's create couple of placeholders, right? And then we can just verify whatever we are just saying, that's basically still valid in terms of the coding, right? So what we will do, we can just create first of all our result list here. Integer result equals to new linked list. Okay, so what are the two observations here? Let's quickly check our observations, right? So observation is parent node and BFS, right? So parents node, we need to keep track of the parents node, and then this is parent nodes, and then another is the BFS. How we can keep a track of parent nodes, right? So let's see. So if we have to keep the track of the parent nodes, we can maintain basically here the hash table kind of the implementation. Why we need to do that? Because we need some kind of the storage, right? We just pass our node, and that storage should return the corresponding parent, and that's why we are doing this. So key and value, let's say node 3. Who is the parent? There is nothing, right? So we can just say, okay, 3 parent is 3 itself, or we can just assign null as well, right? There are two options. I mean, we can do either. We can say, okay, 3 is the parent of it itself, or there is no parent, we can assign null. Who is the parent of 5? This is 3. Who is the parent of 6? This is 5. right? Who is the parent of 2? This is 5. Similarly, we will just keep doing. So you are observing here, every node is the key and the corresponding parent is the value. So value can be, I mean, one more than one node, different node can have the same parent. In this case, 6 and 2, they are having the same parent as 5. So let's store this in the hash table kind of structure because it is a little bit intuitive and a little easier to maintain. So let's say build parents map, and so this is tree node, right? So map would be tree node comma tree nodes key value pair. This is parents map equals new hash map. Build parents map here, and then just pass our root. Initially, let's say parent itself was also root. So root parent, we are assuming that it's root itself, or another option is we can pass it null as well, right? So it depends. Uh, it depends upon the developer what how we want to implement. So let's say private void build parents map. All right. So let's do this tree node. Let's say this is node tree node. Let's say this is parent, and then this is map. So map is tree node parents map. All right, so let's check this. If node equals to null, this is base condition, then go ahead and return, do nothing. Otherwise parents map, we will put corresponding parent itself, right? So what would we do? Node comma parent. All right, now let's call this method recursively. So why we are calling recursively? Because we want to do the same thing for left and right. So node dot left, let's come back here again. So node dot left, let's say node dot left is 5. Who is its parent? Its parent is node. So let's say my node is 3, node dot left I am passing 5 and node is 3. So I will doing the same thing. Similarly, node dot right is 1 and who is the parent? Parent is 3. So that's the same thing I will be doing here as well, right? Node dot left node and then parents node. So yeah, fairly easy to understand, right? So node dot right node parents map. What this recursively, it will just keep pulling. Once it will find node is null, then basically it's not going to do, and that's where we want to break our condition, right? This is the base condition. Now let's quickly do the BFS. So BFS, what we do, we just maintain the queue as we saw in our whiteboarding, right? Oh, this is queue only, not hash map. So new linked list. So this is queue and then linked list, and then what we will do, queue dot offer here. Let's go ahead and offer to the target, offer the target to the queue, right? And let's check while queue is not empty, right? This is how we walked through, right? The implementation part. So if you remember, like this is how we were walking through that, this is how it will work. So the same code we are writing here, we just inserted the target. Now we will poll from the target, and then we will just go label by label. So let's take another variable that's called the label itself, right? So int label equals to 0. Tree node, let's poll this guy, node equals to q dot poll, right? Once we poll this guy, and in fact what we need to do here, if you see here, so let's say 5, right? So we are just polling 5 and then we are just putting its children, right? 6 2 3 or whatever. So we have to do it for 5 only. For 6 2 3, what we are doing, we are doing every for 6 2 3 itself. So we are doing here, we are doing this iteration one time, I mean for 5 itself. Here we are doing the iteration 3 times because 6 2 3 3 elements, and again it's 7 4 1. Even if we need to do then only the 3 elements, we have to do 3 times, right? For the 3 people, for the 3 numbers here, right, inside the queue. So what does it mean? We have to take the size of queue and the number of size, whatever the queue contains, that number of the time we have to poll that, right? So whatever I'm polling here, I need to do it in as the whatever the number of elements inside the queue. That's what I mean. And this is pretty standard BFS template, so it is nothing new, but I just wanted to uh, explain it basically a little bit more clear. So I is less than size and I plus plus. So let's go here and let's see. So node, right, 5. For 5 it will just do one time, right? So for one time simultaneously it will check, okay, whatever the child and whatever the children of 5 and the parent is there, it will just insert here. Similarly for 6 to 3, again the size would be 3, so it will do the same thing for 6. It will do the same thing for 2. It will do the same thing for 3. So it will do the 3 times. That's why we are taking I is less than dot size. All right, so now let's do this. So node dot left if it is not equal to null. And remember the important point is basically we have to maintain the visited thing. So let's take here the set, because set is little easier to just make sure that there is no duplicate. So duplicate means there is no visited again, right? There is no node that is visited again. So we will put the target in the set. Okay, so let's say if node dot left is not equal to null, and then visited dot contains, right? If visited does not contains node dot left, right, then what we are going to do here, we will be simply queue dot offer. Let's do this, node dot left, and visited dot add node dot left. Let's do the same thing for the right side as well, right? Same thing. So let's do this right. Let's do this right, and then node dot right here, node dot right here. All right, let's do the same thing for parent as well. As remember, we were doing the all the direction, I mean both the directions, right? So this is the target, we are going down and we are going up as well, right, at the same time. So for the 5, you see here, so for the 5, let me take the different color, maybe red. So for the 5 here, we were taking child, right? So children is 6 and 2 and the parent is 3. So we are doing uh, by direction, I mean both the direction, from target downside and upside as well. All right, so let's do the same thing here as well, and let's take tree node, parent node. We are already having the storage, and that storage name is parents map, right? Get, let's pass our node, and then it will return us the corresponding parent node. And let's check this parent node is already visited or not, right? So if visited, so if vistate does not contains parent node, then what we will do, we will just add vistate.add parent node. And why we are not checking left and right? Because this is the parent, right? So let's say here, so for 5 we already checked left and right here, left and right, but for parent we are just checking only parent, right? Parent, if it is not visited, then we will put, right? Again this parent will become the node, right? So in this loop again we will check, okay, size, and then whatever the size, this parent will become the node. And then for that parent, like for example this parent, right, this guy 3, so for this 3, we will again go through the child, right? So we will again go left and right, and then again we will check for one parent, right? Who is the parent of 1, right? So the parent of 1 in case is 3, right? But 3 is already visited, so unfortunately we will not be putting inside the queue, but this is how our algorithm should work, right? So no need to check again left and right for parent, right? That's what I mean. All right, so once we are done with that, then we can just increase our level, right? So this is one level. So this block is whenever we are traversing I is less than size, this is the one set of the queue, one set of the numbers inside the queue, and then we will just increase our level. Once we are done with that, then you remember, like I said, like if once this label becomes equals k, right? Is it small or capital? Let's see. This is capital K. Okay, so if then what we will do, we will get list, right? So get list is nothing but it is a small method we can create. It will just get inside from the queue. So in the last, whenever the label is 2, we were having 741 inside the queue, right? So we will get from the queue, right? And uh, let's say for example we don't find any eligible or anything, then in that case we need to return the empty list, right? So we created here the result, right? So we will return result. Okay, now let's create another that is small method as well, and that is list of integer. Get list. How it will get the list? Will get the list from queue, tree node queue. So list of integer, and then let's say it's called res linked list, while this queue dot is empty. If queue is not empty, then res dot add what we can do, queue dot poll dot val, because remember this queue is holding the tree node kind of the object, right? So now return res. Okay, so that's it. I mean, from the queue, just get from that list, get to that list. So this is the idea that we were discussing using whiteboard, right? Let's quickly check for the compilation error if there is any, and then we can quickly correct those compilation errors, and then we can move forward, right? So, but this is the basic idea. And complexity wise, it would be, I would say, like we are just going through each and every node, right, in the up and down, right? So whatever the number of nodes, that would be our time complexity, and space complexity is also basically we are maintaining this queue, so it will be order of n. So don't worry about this output, we can correct that. So we are skipping one, right? So let's see what is wrong in our logic. Okay, so target we are putting here, and then listed does not contain node dot left, node dot right, node dot right, this one, node dot right. And for the parent node, get node listed does not contain. Okay, so this is the mistake we did here. We need to we need to again offer this basically parent node as well, right? Why we need to do that? Because again we will go here. So in the queue, remember, we were just taking the 5 and we were putting 6, 2 and 3. So the mistake we were doing, we were not putting 3, right? We were not putting 3 inside the queue. That's the mistake we were doing. That's why we were getting the wrong result. So we have to put the parent as well, right? Right? So just track with that visited set as well, whether it's visited or not, and just put inside the queue as well. So fortunately there was no syntactical errors. That's good, and it's working fine as well, so that's great. And let's quickly try to go ahead and submit this one, and let's see if it is going to work. So great, this is working. So quickly, just quick summary points before ending this video. One thing is basically we need to observe like the target node. The target node, we have to travel some of the distance, right? Then the distance is given here, k equals to 2, right? So now we need to collect the couple of facts and observations here, and the important observations here is we can go either basically both the directions, not the either, but we have to go upward from the target and we have to go downward as well from the target. And that's why we need to keep the track of the parent node. Once we know this observation that we are going upward from the target and we are going downward from the target as well, then it comes to the conclusion, okay, we need to keep the track of the parent node for every node, right? Otherwise, how we will go up direction? Once we go to up direction, then we should know the parent, right? And then once we know that we have to keep the track of the parent nodes, then we need to think about some storage, where we will store the parent. And that's why we took here the hash table kind of the implementation, right? Because it's little easier and intuitive. So for every node we are just having a corresponding parent, so that we will just tell our hash map, okay, this is my node, let's give me the corresponding parent. So this will immediately return me the corresponding parent, and that's the advantage of this hash table data structure. So we are just using the hash table here. Now once we know this parent, and then we have to keep basically little bit more focus on the how it's working, right? How it's working means it's going neighbor. First of all, it's just traversing the corresponding neighbor, and this is how we just use this strategy in the breadth first search. And that's why the key observation here is the breadth first search, but not depth first, right? So depth first, what we do, we just go deep. We just don't worry about the corresponding neighbors, we just focus one neighbor, neighbor by neighbor, neighbor by neighbor. We will just keep just traversing till the end. This is the depth first search. But here what we are doing, we are just traversing the breadth. So breadth means we are holding one node and we are just checking what are the my neighbors, right? Once I'm done with the neighbors, like for example 5, I'm just traversing the neighbors, right? So neighbor is 3 and another neighbor is 6 and 2, right? Again I'm traversing, I'm just holding this 6, 2 and 3 and just traversing those neighbors. And this is the strategy we adopt in BFS. So once we know these 2 points, we can build our algorithm. And last but not least is this one, like how we are actually going to solve this problem. So we are just taking the queue, and this is the queue basically for each level, right? So this is the level 0, this is for the level 1, and this is for the level 2, right? So this is nothing, right? So 0, and then for 0 level we are having only 5. For level 1 we are just inserting our children, right, into the queue, and the parent as well. And for the level 2 we are again inserting the children and the parent. Once this level will becomes k, then we are returning whatever inside the queue. So that's what we are doing. The mistake we were doing earlier in our queue, when we were getting the wrong answer, we were not inserting the queue the parent, right? So that's why we have to insert the parent as well. So hopefully this is useful. Thanks a lot. Bye.